Sorry about that. Okay. Yeah. So our tool of choice for this kind of like tabular, do you know, is it working? All the way to the start again? Yeah. But you don't have to repeat. Yeah. Because the audio is on. So let's make sure that they have some feature. Okay, sorry for that. Yeah, so our tool of choice for this kind of tabular data, so like rows of data, will be Pandas, which is. Okay. So Pandas is a Python library that will help us manage tabular data efficiently. And in Pandas, we have data that is stored in series and data frames. So series are like just lists of data. Start from the beginning. Okay, sure. Oh, okay. Sorry. All right. I'll just go through again from the start. Yeah, this is Intro to Data Science. I'm Javier. So yeah, the quick disclaimer, this is Intro to Data Science, not AI, not machine learning, nothing fancy. We'll just cover some simple stuff like plotting graphs, like linear models and classifying stuff. And the workshop aims to give you an understanding of the data science lifecycle. And yeah, so once again, we'll be using Pandas to load and access our data with Python. Then we'll also be doing some simple exploring of the data with matplotlib and seaborn, which will help us plot graphs, and we'll then look at how to interpret those graphs. Then we'll look at data modeling, which is like drawing best fit lines. That's called regression, and also classification. I'll go through into these more later, but yeah. So data wrangling, this is where we would analyze our data. Before we even analyze our data or plot our data, we need to load it into the code. And the first thing we'll do is clean the data usually, which is like removing missing values or empty rows. But that'll be skipped for this workshop because it's not too important for the understanding. And our tool of choice for this will be Pandas. And Pandas is a Python library that helps us manage tabular data efficiently. And in Pandas, we have data that is stored as series and data frames. So series are like lists of data. So maybe like just the number for each person, maybe there is a series corresponding to their attributes, maybe like their hair color, their shoe size, all that kind of random stuff. And we also have data frames, which are tables of data. So it can be like a series of a series in a way where, yeah, sure, sorry. So yeah, each data point is identified with an index and a column. And we'll look at some actual code so it's easier to understand. I'm not sure if you will send this link in advance, but I'll just show it on screen to be sure. Give me a second. Okay, so if you opened up this Ipython notebook, so yeah, if you have the link and you can open with Google Collaboratory, that is the online Python runtime that we'll be using. So it's standardized and easier for everyone. I'll leave that up for a few seconds. Yeah. So the first thing we need to do when we're using any library really is to first import it. So, oh yes, and yeah. It will give you this warning when you try to run it, but just click run anyway. It's nothing harmful. Yep. So it's run. So the first thing we do is to load the data. In this case, our data comes from this URL, which is of a wine data set in this case. And we can do the loading with pandas.readCSV. CSV is the file type. And when we run that, we get our data frame, like I mentioned earlier. So a data frame is just rows and tables of data. You can actually look through each individual element if you wanted to. And on the right, on the left here, you can see these indexes. So the index refers to the number of the index of the wine in this case. So the 0th wine, the first wine, and so on. And we see that we have 4,898 rows, which means that we have that many number of different types of wine in the data set. Yeah. And then on the top, we can see that we have these labels like fixed acidity, citric acid, all that kind of stuff, alcohol, quality, pH. All those are the columns of data. So if we were to access like 0 and then quality, we would get 6 all the way on the other end. So that just tells us that the quality of the 0th wine is 6. We can, obviously, when we want to access the data, we also use it with code. We can do that with this log function. Log is basically how you locate the data. And when you say log 0, you're getting the first row. Yeah. And one thing to take note here is that log returns, or in this case, it returns a series. So on the top, we had a data frame, and then now we have a series because it's returning just one row. And you can see it has all the attributes that the row and columns initially had, just that this one is only of the first wine. You can see here, if we call type, we see that it's a series. We can also access the columns. So like if we have log, and then we have a colon, comma, we can put the name of the column which we want to access. In this case, chlorides. So it gives us 0.045, 0.049, etc. And if we go back to the original data frame, yeah, you can see that in the middle. That's exactly what we got, 0.45, 0.49, all that. And we might need to access multiple rows, and we can do that by passing a list of the indexes. So practically, this would be like when you have just specific maybe elements that you need, and you want to ignore everything else. This is how you do it. This is how you would do it. And yeah, you can see that this time it returns a data frame, not a series, because there's more than one row that is needed. And it's exactly the same as the original data frame, just that it's just the subsection that we wanted. And if you call log again, but we put a list with one element, we actually get a data frame just with one row. So this is different from when we called log with just the element directly. The first time it returned the series. The second time it returned a data frame. We can do the same for columns. So if we wanted chlorides and the pH row and the pH column, we would call log colon, comma, chlorides pH. And that just gives us the same data frame, but only with the chlorides and pH. we can actually do both at the same time. So if we only wanted certain rows and we only wanted certain columns, we can just put both of them together and we can access just 0 to 199 and just the chlorides and pH. So we also have iloc, which is similar to loc in that it uses the numerical indexes instead of the names. So if you remember the chlorides, that was on 0, 1, 2, 3, 4. It was on the fourth column. So if we only knew it was fourth column, we could call iloc instead of giving it the name, which was chlorides. And once again, we can do both. We can access the rows and columns at the same time with iloc, just as we did with loc. And a nice little shorthand that we have is that when we just want to look at the columns, or just one column, we can just call df, no need iloc, no need loc, we can just put the column that we want. Similarly, we can pass a list of columns that we might want. And that just gives us that, yes. So I just want to reiterate the reason that we are looking at these functions is because when we are given any data set or any real life data set, we are not going to use everything in there typically. There will be some things that we want to filter out or stuff that is not needed or not relevant to us. So with these functions, it can help us to remove and filter out things that we don't need or don't want to see. So just a short exercise for you is to filter the data frame so that it only contains even numbered rows. So earlier we had a way to filter to 0 to 199. One thing that we might want to do is to access just the even rows. So just a short exercise, you can try it now.
So you pick out if you can, just pick out and also once in a while get the participants.
But there's no way I can see the chat because I'm sharing on this screen.
Okay, sure. Let me.
Yeah, that one.
So these are the indexes. And what we want is just the even one. So just this and just this.
Yeah. So there are two numbers. There's even, and then you just want to filter the two.
So we just want to like hide this and hide this. We just want this and this.
Then want this to be. Oh, okay.
Currently it's okay. Just remember that we may be wondering why you're not talking because we can't hear you.
Okay.
Yeah.
Okay, so I've left for a bit now. I'll just go through two possible ways to do this. So one possible way is to just, with the element if you remember the list accessing, we just make a list of everything that we need. In this case, just the even numbered ones. Then we pass that to the ilog function, which will give us exactly what we want. So you can see it only has 0, 2, 4, all the even numbered rows. And another possible solution, if you're familiar with Python indexing maybe, you can actually do this, which is just saying get everything but skip 2. So it will go 2 at a time, and yeah, it gets us the exact same thing. So I'll just pause for any questions if you guys have any.
So what is the purpose of going through the exercise then?
So it's just like a quick recap, I guess, of everything.
Wrangle the data.
Yes, so this is just a way that is for us to filter the data. It is a very simple way, but it can help us to suppose like our data set, we only want to look at alcohol and quality. So this is how we would do it.
So how you wrangle depends on the purpose, right?
Yes, so depending on whatever purpose we have for the data, we will do different manipulations to it. Okay, I'm not seeing any questions in chat, so I will move on to the next section. Okay, so that was data wrangling, which was just to help us filter the data, to help us really locate on what we want to focus on. And now we can look at data exploration, which is the next step. And yeah, before we can model or analyze the data, we want to understand our data. So by making useful plots and statistics and just really playing around with the data, we can get a lot of information about it, and we can uncover patterns in the data, anomalies like missing values, and we can find points of interest. And this allows us to get a deep understanding into our data, and is very useful when we are modeling the data, which is the next step after this. So
So does it include exploration?
sorry?
It means what do you call that? You got to a point and then what do you call that? Extrapolation.
Well, okay, so stuff like extrapolating data points, that is more under modeling. So that will be, specifically, that will be regression, which we'll cover later. So one thing that we can do is, once again with the data frame, we can call .describe. And by calling .describe, it actually gives us these few statistics of the numerical data. So if this was a categorical data, it wouldn't really make much sense to ask for like the standard deviation. But for numerical data, we have this nice summary. So the first thing that we can see is that it returns another data frame. So count, it returns the count. And the count is just how many elements there are. So again, there's that many number. And the next thing we see is the mean. And the mean is just the average of the entire row or column, sorry. So SDD, that is the standard deviation. It's how spread out our data is.
Plus and minus certain percentage. Just like the bell.
No. So
So it's a standard deviation is like you deviate from the norm, right?
So standard deviation, that would be the for one particular value, we can have a calculation of how much it deviates, and then on average, how much do the entire data set deviate from the mean. That it would be the standard deviation.
Yeah. So for example, in the bell curve is plus and minus 10% or what? To the right is and to the left is something.
much
It's
more like,
plus, to the right is plus, to the left is minus, right?
yeah. So yeah, min is the minimum value that occurs. So 6.3 is the smallest fixed facility that we'll ever see in the entire column. And then we have the 25, 50, and 75 percentiles. It's basic. So the 25 percentile is the value, so that 25% of all other values are smaller than it. Then the 50 percentile is similar. It's the value, so that 50% of the data is smaller than it. Same for 75. And the 50% percentile is also called the mean, the median. So it's like another way of thinking of it. It's another kind of average in a way. And then at the end, we have the max, which is just the maximum value. Okay. So that was for numerical data. For categorical data, we will also we would call like stuff like unique, which I'll go through later. And what we can also do is plot the data and draw graphs. So things like a histogram, that is histogram, KDE, and box plot, those help us look at single variables of data. We also have multivariable plots, which will look at two variables or more at the same time and show us any interactions they might have. So we might have a scatter plot, which is just saying for each x and for each two of these, we put a dot where the coordinate is.
It's just like a graph and one straight line and then all the scattered are all.
Yeah, so we just plot a point wherever the value is. Again, we have the KDE, which is the kernel density estimate. I'll go through what that means later. And then we also have a categorical box plot. So I mentioned the histogram and KDE. So the histogram is the bar chart that you're looking at on the left. Basically, it's just saying how frequent is this range of data. So you can see the 150 to 170, that is on there. And this section of this range of data, it has the most, it's the most frequent, it's the most common occurrence. And you can see it tails off at the end. We also see the smooth, okay. And the smoothened one, that is the KDE. So it's similar to a histogram, but it's plotted smoother. And it's called a KDE because it's estimating the curve. So these two just gives us an idea of what our data looks like on a trend. So we might see that there are a few values which are very common, like the middle, and we might see that there are a few values which are not as common, like at the ends. We also have the box plot, which is just a quick summary. If you remember the .describe function, the box plot is similar to that, but it just gives us a graphical representation. So we can see the upper extreme, that would be the maximum value. And the upper quartile, that is the 75 percentile. The median is the 50th percentile, and so on. So the whisker is just drawing a line to show us where the data ranges. And yeah, we also have outliers, which are drawn for us. If they stray too far from the center of the data, it gets drawn as an outlier instead. So these plots help us to understand the just single variables and how the individual variables and values are spread.
Where would you foresee an outlier?
Okay, so in this case, the outlier is calculated by saying if it's too far away from this central range. So if it's 1.5, or if it's more than 1.5 away from in this case the lower quartile, 1.5 of this range, of this lower quartile, then it's said to be an outlier. So technically,
It's a fix. It's a formula already.
yes. So technically, it could not be an outlier, and that's the issue with a fixed formula. But in general, it gives us just an understanding of this data point is extremely far away from the center. So for even in a normal distribution, this formula will say that about 1%, if I'm not wrong, of the data is an outlier.
So it's still within the norm that you have outlier, right?
Norm, sorry.
It's still within the norm. Let's say 1% that is in the outlier area.
So yeah, 1% of a normal distribution will be an outlier.
So 1% is something you can tolerate.
Yeah. Okay, so again, we'll look at some actual code. And in this case, it will be exploring the Ipython Notebook. If you have the link, you can go to it. If not, I'll be showing it on screen.
Remember, they have more online participants than inside, so they won't be able to hear the question posed by them. So when we put some time, we try to repeat the question for the online participant.
Okay, so again, yeah, just run it. Okay, so this first chunk of code is just the same from the earlier part. It just loads the data into the data frame. So like I mentioned earlier, we have the .describe function that gives us these useful statistics of the data like count, mean, standard deviation, all that. So yeah, again, how you read it is that the .describe returns another data frame from the original one, and the rows are the different types of statistics, and the columns are the original columns. Okay. So for categorical data, like I mentioned, we have another function, value counts. So if you look at the original data frame, we have this quality column, and the quality is given as 1, 2, 3, all the way to 9. So, and it's individual numbers. It's not continuous. So it doesn't really make sense to ask about like the standard deviation of these categories. So instead, we can call value counts. So we can read this as there are 2,198 occurrences of the quality 6. There are 1,400-ish of the quality 5, and so on. Yes. So now we can look at some plotting of the data. So we usually do this with the Pandas.plot function. That gives us it returns a matplotlib graph in this case. And yeah, like I mentioned, the three common types we'll be looking at are the histogram, the box plot, and the KDE, which is similar to the histogram, but it's smoother. So before we use it, we have to import it. Okay. Yes. So if we look at just, I guess once again, if we just call this, we'll get back a series. But we can also, from the series, call .plot. And then we specify the kind of the plot. In this case, we will plot a histogram. And that gives us this. So we can see that the 6 to 7, like we saw earlier, that is the most frequent occurrence. And all the others are less than it. And if we change this kind attribute to say KDE, we get a smoother one. You can see the similarity between the two plots. So the bottom is just smoother. The value sum to 1 because it's a density, and it gives us a estimated an estimate of how it looks like if it's smooth. And one thing I want to touch on is that, okay, so this chunk of code, you don't really have to understand it, but it just generates this picture for me. So if you look at these three histograms, what I'm doing between these is keeping the data the same, but I'm changing what's called the bin. So the bin is just how often we group together the data. So if we have a very large bin, we see that it's just 1, 2, 3. It's just these three main spikes. But when we have a large bin, it removes the finer details. It removes the finer details of the data. So it might be what we're looking for, but at the same time, it might be misleading. So we really have to look carefully at when we plot something, what is the parameters that we're asking it to plot as. So even though these are all the same data, by changing this one attribute, we're getting different plots. So, and on the last plot, it's a little more noisy because we're almost not grouping it at all. And yep, with too big of a bin, we actually lose a lot of the detail. But with too small of a bin, it can get a bit noisy, so it's harder to interpret. So yeah, KDE is the smoother one, which is this. They also have a similar problem. You can try it for yourself. It's called the BW method. You can just do that for yourself, yes. So yeah, back to the plots. We also have this box plot. So the syntax is the same. It's just series, get the series, dot plot, kind. In this case, we want a box plot. So we can read this as this bottom line. That is the minimum value that we'll see. And at the bottom is the name of it. The green line is showing us the median, which is the 50th percentile. This top part is the 75th percentile. And the final part here, this is the maximum. And it's the maximum before it starts saying that the points are outliers. And everything above that we have termed it and we've called it an outlier. So for the residual sugar, we can see that there are about 4 outlier points that are way higher than everything else. And that might be something that we have to take into account if we're doing modeling of the data. So that was just for one individual attribute, but we also want to look at 2 attributes at the same time, because that's how we see the relationships and the interactions between the data. Sorry. Yeah, so we have an understanding of the individual features of the data, but we also want to know of how they can interact with each other. So one simple way you can do it is with the scatter plot. And basically, for each data point, we take one attribute as the x coordinate and another attribute as the y coordinate. So we have a function here, plt scatter. It's no longer using the data frame.plot syntax. But basically, we're saying that we want the x coordinate to be the data frame, then the series citric acid, and then we want the y coordinate to be the fixed acidity. And if we call plt, which is pyplot.scatter, that's the scatter plot, and then xy, we get this. So how we read this is that this one dot, that is about 1.25 on x. So it has a citric acid of about 1.25 and fixed acidity of about 8. And then we just repeat this process for every single one of the 5,000-ish data points that we have. And one issue is that for when we have many data points like we have, the scatter plot can get a bit messy and it's harder to see. So we can do what is the KDE plot again, but in 2 dimensions this time. Give it a second. So you can see the shape is about the same. But what this one is telling us is that a lot of the points are concentrated here because there's a lot of lines. It's a contour line. So as you go towards this center, there are more and more points which have this value. And you can see this chunk of values here. That's the nice thing about the KDE plot, is that it makes it very clear where we have clumps of data. And one more thing we can do also is to do the pair plot function. Because right now we're choosing one attribute as x, another attribute as y. And with pair plot, we can just automate all of it to say for each x, for each y, we plot one. So yeah, that's the pair plot function. It gives us a very big graph and it takes quite a while to run. And yeah, I'm going to zoom in because it's a bit hard to read. Can I even, sorry. I guess I can't zoom in too much. Okay. It's a little bit hard to read, sorry. But on the bottom, we have what is plotting as the x coordinate. And on the top, we have, on the left, we have what is plotting as the y coordinate. So I don't know if you can read that, but this one says density, for example. And you can see that along the diagonal, these plots are different because it doesn't really make sense to plot one attribute and against itself. So instead what happens is that when we have along the diagonal, we plot a different kind. In this case, we specify it to be the KDE. So with this plot, it's really hard to see really. But for example, one thing we can look is that these two attributes, they have some sort of correlation between each other because you can see them going up. And if you read off it, the first one is, on the y-axis is the residual sugar, and on the x-axis, it's the density. So at a glance, we can pick out which variables have correlations with one another. And like I said, one of these is the residual sugar and the density. So this only really helps us find correlations between two variables. And when we have 3 or more, we might need to do more complicated stuff, like changing the color of each data point to represent a value. So with this data set specifically, we might want to predict the quality of the wine. So let's try to target our exploration towards the quality. So one way we can do this is to just say for each of the attributes, we want to plot maybe a box plot of the quality versus that attribute. And we just run this short part of code. Okay, so that just gives us all these plots. And each plot is the box plot, where the bottom x is the quality, and the y is the attribute that we're looking at. So for most of these, there isn't really much of a correlation. But if you look at the very last one, we see that alcohol has an interesting trend with the quality. So when we're doing the data modeling step, this is something we might want to remember. And we might want to specifically remember that the alcohol and the quality have some sort of relationship with each other. And like I said, when we have 3 variables, we might want to plot them together. So we've already used our 2 dimensions. What we can do is change the color of the data point. It's a bit messy, but basically, we're plotting a KDE again between the alcohol and total sulfur dioxide. And this final part is to change the hue. So if the quality is greater than 5, then we will have it separate from if the quality is less than 5. And yeah, it gives us these 2 different KDEs. And yeah, on average, we can see that higher quality ones have a higher quality ones have a higher alcohol content but both of them have similar sulfur dioxide content distributions. Okay, I'm going to pause for questions if there's any in chat. Okay, nothing. I guess we can move on first. Okay. So now we can actually do some of the modeling of the data, which is like the regression and the classification. So in data modeling, there are mostly 2 types of problems, which are regression and classification. So when we want to perform regression, it's like estimating a dependent variable from everything else. So linear regression, for example, is just about finding a best fit line. And classification is about classifying a data point from all the variables that we can see. So one subset of that is binary classification, where we just want to determine which of 2 classes a data point should be in. So for example, cats versus dogs, that would be classification. But predicting maybe an animal's foot length from its ear, that would be regression. Yeah. So linear regression, like I said, it's about finding the best fit line, really. And a bit of math here, but let's say a data point is xy, and we want to find the best fit line, which is y equals mx plus c. In essence, we want to minimize the error between y and big Y, which is what is estimated. And by minimizing the error, we find the best fit line. And there are a few algorithms for determining the best fit line and minimizing this error. But when we are using the libraries, it's extracted away for us, so we don't have to deal with it. Instead, what we can do is just ask it to help us find the line. So yeah, you can see the short clip of a algorithm finding the best fit line. And after a few iterations, it does converge on that one line. And when we have more than one independent variable, usually we just have different coefficients for the different attributes. So yeah. When we're doing data modeling, we also have binary classification. And logistic regression specifically is a way to perform binary classification. So the name is a little confusing, but yeah. So like I said earlier, binary classification is classifying between 2 different attributes. So the way we can do this is to assign 0 or 1 as our 2 classes. And then we take the linear regression and we put it into what's called a sigmoid function. Basically, the sigmoid function helps us to make sure that the output of our prediction is between 0 and 1. And once again, we minimize the error between the predicted, and it will help us to predict between 0 and 1, which are our 2 classes that we assign to it. Okay, we're going to look at code again. So in this case, we're going to look at modeling.ipython notebook. It has some stuff on how we can do linear regression and logistic regression. Okay. Okay, so yeah, we run this first part, which is just importing all the libraries that we looked at so far and getting the data from the same link as always. And the first thing we'll look at is linear regression. So, and in the earlier step of data exploration, we already saw that residual sugar and density had kind of a linear relationship and they had quite a strong correlation. So we can try to put this into numbers with sklearn. So the first thing we do is import the model, which in this case is a linear regression. And basically this function helps us to do all the fitting of the best fit line. So we don't have to do it ourselves. And we can just focus on what we want to, which is analyzing the data. So the first thing we do is to extract out the x and y. So from the residual sugar, we want to maybe predict the density. So we set the first one as x and the second one as y. Now the next thing we have to do is to initialize the linear regression object. We can do that with just linear regression in brackets. So next we can call the dot fit function. The dot fit function abstracts away all of the math that we looked at earlier. So all we have to do is just call dot fit and it will run for a bit and then return a nice fitted line. On the bottom, we can do some visualization, but yeah. Yeah, so after the dot fit function was called, it fits the linear regression to these two values which we picked out. So from the residual sugar, it plotted onto the density, and you can see the line that it fitted. So with the regression, we can actually get the exact numbers that are found with the dot coef. So in this case, coef is actually a NumPy array, which is just a list of numbers. And it's a list of numbers because this function works for multiple variables also. So in this case, we only have one variable, so we just access the first coefficient. That is multiplied by x, and then we add it to the intercept, which is found with dot intercept. So we actually can find the score of this fitting with the dot score function. So dot score just helps us to figure out how good of a fit this line is. And in this case, it's 0.73-ish, 0.703-ish. And the maximum score that we can get is 1. So this is quite good, I would say. And a score of 0 means that it's as good as just predicting the mean value for everything. So if you just took the average and that was what you fit it to every time, that will give you a score of 0. This is called the R-squared metric. You can read up on it if you want. And so we just looked at linear regression, but we can also do logistic regression, which recap is not really regression, it's more of binary classification. So again, we can, from sklearn linear model, we import logistic regression. And in this case, we want to predict between two different classes. So two classes that we can choose are maybe if the quality is greater than or 6 or less than 6. So that will be our target variable that we want to predict. And since from the data exploration stage, we knew that alcohol seems to have a high correlation with it, we choose that to be our variable to look at. So again, we initialize the logistic regression. We call dot fit again. So notice that the syntax is basically the same. And that's the nice thing about sklearn, is that much of the syntax is the same. So we don't have to focus on the math or remembering all these libraries. We can just remember which algorithm we want to use in which case and use it. So again, after it's fit, we can do some visualization. And this is the prediction threshold that it's giving us. So for an alcohol content of less than about 9.5, it will say that the quality is smaller than 6. For an alcohol content that is greater than that, it will say that the quality is more than 6. So it's predicting between the two classes, which is less than or more than 6. And the reason that it's making this decision in a way is, well, if we look at the box plots of less than 6 and more than 6, we can see that, yeah, there is a trend here where an alcohol having less than 6 has a lesser alcohol content than an alcohol that is sorry. Then when it's more than 6, so when it's more than 6, it's usually has a higher alcohol content. And again, we can print the score. And the score here is 0.69. Again, the maximum is 1, so this is an okay fit. Oh, sorry, there was a question in chat. In the residual sugar, there is one value at almost x equals 70, which is very far away from the rest. How can you determine if it's an outlier or should be left in the data set? So, I see what you mean. So this data point up here, that is, I think, what you're referring to. And yeah, you're right, it is very far away from everything else. So this is where we would, if we had seen this only now, then our exploration stage is insufficient, I guess. But if we were to go back to our exploration stage, usually we will have seen this data point, and then we will have looked at everything else about this data point. So yeah, so we would try to identify, maybe is it just this one attribute that is an outlier, or is it that the entire data point, so the entire wine is an outlier? If it's the second case, then we would usually just remove it from the data set and say that this is an outlier. Or if it just happens to be that this one wine has a really high residual sugar, but everything else is more or less normal, we might want to investigate more or just keep it in the data set. So really having domain knowledge, as it's called, which is understanding of the data in context, that's really helpful for determining outliers and when we're making models and interpreting the data. So outliers are basically determined by common sense and domain knowledge. There is no formula or something. Thanks. I guess there is that one formula from the box plot, which is just saying that if it's 1.5 times away from the, I'll go back to the box plot. If it's 1.5 times away from the center, then we call it an outlier. That is a fixed formula of sorts to tell us if it's an outlier or not. But when we're trying to determine if it's an outlier or not, we really need to understand the data point. We need to understand what does it represent. So there is not really a fixed formula. Yeah. Okay, I'll check if there's any more questions. Okay, if there's nothing, we can move on. So yeah, now we can do some DIY. So this part is really for you to just reconcile everything that I've gone through in the past hour or so. So we're going to look at a new unseen data set. Specifically, it's called the iris data set. It's a data set of different types of flowers and their measurements of like the petal length and the sepal length, the width. So there are just 4 attributes here, so it's not going to be too difficult. But yeah, I want you to perform just the whole life cycle from plotting the data, from loading the data, then to, at the end, classify between the different types of flowers. Yeah. So yeah, if you haven't already, there is the iris.ipython notebook. That is what you want to look at. And so this is the notebook that we will look at. So it's a fill in the blank kind of thing. So it's not going to be too demanding. Basically, just try to recall how, and read documentation if you want, how do you plot the specific plots, and what observations can you make from these plots? And then at the end, can you make a classifier to determine, can you get a classifier working between just any two classes? So in this case, our data set, I'll just run this here. Our data set has three types of flowers. There's the Setosa. Okay. So there is the Setosa, there's the Virginica, and there's one more, which is so there's 50 types of each of the flowers, the Setosa, the Virginica, and the versicolor. And there are 150 rows of, and yeah, there are 5 columns where each one is the sepal length, sepal width, petal length, petal width, and finally the type. So yeah, just try to plot some plots between these different attributes. There are some suggestions down here, and a fill in the blank style here. You can do more obviously if you want, and try to write down what observations you made. And at the end, yeah, get a classifier working just between any two classes of flowers. Just two because we just went through logistic regression, and that is only for binary classification, so determining between two attributes. Okay, yep. So I'll leave you to that. I'll come back and I'll be answering questions for a while. But until then, yeah, just work on this notebook. Yeah, sorry if I didn't mention this, but we're gonna be doing this for about half an hour more. So if you have any questions, you can feel free to put them in chat too. Yep. So there is a question in chat. So for the pair plot number 6, how do you set the hue as the flower type? I'll just quickly load up the notebook. Give me a second. Okay. Okay, so for the pair plot, you supply the first argument you supply is just the data frame, and then the diagonal kind, that is the, remember, the diagonal type. So on the example that we had, we used the KDE, so I'll just put KDE again. So finally, the hue, we specify this by just type the column name of the data frame that you want, or you could do df then get, or you could pass a series with the data that you want. But since you already passed in the data frame, you can just supply the column name. So also, we'll be going through the remaining questions in a few minutes. So that's just how you get that. So if you don't specify the hue, yeah, you can see that if you don't specify the hue, then you just get this. And with the hue, it will separate it into the different colors depending on the different types. Yeah. Okay, so don't know if everyone's back yet, but we're going to go through the exercise. So, yep. So yeah, this was the original notebook that I passed to you guys. Well, except for this one, but never mind. So yeah, in the drive, I'm not sure if you can see it yet, but in the drive, there should be a notebook called iris underscore solution or iris underscore sol. Yeah, this notebook, iris underscore sol. If you just open that, that is the solution that I wrote. So yeah, we're gonna look at that now. So yeah, the first thing we do is run it. Yep, so we run it. And yeah, so this is our original data frame that we got from the URL. And the first thing we wanted to do was just plot the sepal length versus the petal length. So logical thing to do. And yeah, for this, we can just call the plt.scatter function. And we pass it the length of both of them. Now, Seaborn also has a scatter plot function. I don't know if I mentioned that. But yeah, we can look at that later. So with the first two are more or less the same. It's just the different attributes. And yeah, with the Seaborn, we can actually set the hue. Yeah. With C1, we can actually set the hue, but before that, we want to look at the box plot. So sns.boxplot, and x is on sepal length and y is on the type, and it gives us this plot. So yeah, you can actually see this one outlier here, which is interesting. And if we go back to the scatter plot with the flower type as the hue, we can use C1 for that. So C1 scatter plot, it's slightly different name, but yeah. And so we set the sepal length as the x, sepal width as the y, and then we pass in the hue parameter, which we give it as the type. So on each type, it gives it a color of its own, and that allows us to see the general pattern between the two. And just one more, we also have the petal length, sepal length, and hue as the type again. So we also have the pair plot, which is a lot faster to run this time because the data set is smaller and there's less attributes. So yeah, again, we can use hue here. I like to use it because it helps us to see the different clumps and the different patterns in the attributes that we're trying to predict. So, yep. So for the observations, you could write stuff like, I guess, sepal width and sepal length are correlated, stuff like that. And if you actually look at the petal width and the petal length, they seem to be more or less linear related. So and yeah, so these observations are just nice to list down so that if we're doing any modeling, we have a reference to all the insight that we gathered from this stage. And the final part that we wanted to do is to get a classifier working between two classes. And so this is actually a Boolean indexing. I'm not sure if I went through it, but basically just filters out all the iris setosas because yeah, it's a really distinct class, so it's really easy to distinguish. So for a bit of a challenge, it's always nice to do it a bit harder. So if we try to distinguish between the versicolor and the virginica, we're going to have a little bit of a harder time because you can see that they are not so distinct, while the setosa is basically a class of its own. So yeah, we set the x and y as the different attributes, and we call it a logistic regression. So in this case, I picked the petal length to be the one attribute that we try to use to predict the class. Because if you look at the different plots, you can see that the petal length actually has a very nice line right about here, which cuts the class right in two. So it's a really good attribute, just a single attribute for classification. So yeah, if we run the logistic regression and fitting, we can get a score out. And in this case, it's 0.93, so that's really good. And just one more visualization where I just have a bunch of inputs to the logistic regression. And so if we input all the petal lengths, we see that this is how it's its decision boundary. So less than a 4.9-ish, it says it's a versicolor, and more than 4.9-ish, it says it's a virginica. So this is what it's doing to distinguish between the two classes. And if you look back at the original plots, you can see that it does really seem like that is how it is split. And yes, so there's another linear regression which you can do for fun if you wanted. But because we said that the petal length and width were quite correlated, you can just do a simple linear regression to find what this relationship actually is. And yeah, just one more function, SNS reg plot. It's a regression plot. So if you just want to get a plot data and linear regression at the same time, you can use this function. It doesn't really give you the coefficients, but it's just nice for plotting it really quickly. And yeah, you can see it has a really high score, which means that it is quite well correlated, linearly at least. So that was my solutions at least. If you have any questions, you can ask them in chat. So if there are no questions, then yeah, this is basically the end of the workshop. I really hope you guys enjoyed this 2 hours where we went through the whole data science, well, not the whole, but most of the data science lifecycle from data wrangling to exploring, then up to this point, which is predicting between the different flower types. Yeah, hope you guys enjoyed it, and there is a feedback form, which I'm not sure where it is. I'll send it out later. But yeah, thanks for coming, I guess. There's one more thing, which is, I have to say this. So if you're looking to upgrade your skills for career progression or transition, but not sure where to start, then you can speak with a Skills Future Singapore Skills Ambassador to identify your needs and gaps and gain useful tips and advice on how to kickstart your skill search. There's a QR code you can scan if you want to learn more. So yes, there is a feedback form here in the QR code. And if you would like to find out more about the wide range of training courses and resources, you can access the Skills Future portal, which is also in the QR code. So yeah, thanks. Sorry. So yeah, that's the end of the workshop. Thanks for coming.